Today we are moving on to another big chunk of the theory underlying machine learning, so calculus. So we are going to look at basic definition and the concept and operations. So derivatives. So when you take the derivative of a function, so 미분 in Korean, this is basically measuring the rate of change. So you have a given function and you want to move a small amount of input and you want to measure the changes in the output. So the ratio between input and output becomes your target value. In terms of notation, you can write this derivative in this way. So you want to measure the change in the input. And you compare that against the change in the output. So the ratio between these two becomes your target value. One other important thing is where you want to check out this change rate at certain moment. So where you want to measure the change in the input and output, but the amount of change is going closer to zero. This is the concept of derivative. So where you are starting from a visible change in the input space, and the change in the output space is also visible, but you want to narrow it down by taking the limitation. So delta x is just saying the change in the x spaces, in other words, change in the input, and you want to make it close to zero. Something like this. And eventually, this change rate becomes the slope of the tangent line on the function. So you pick a spot and draw a tangent line. The slope of that tangent line becomes the derivative value. So here comes some example where we take the derivative of function here, and we can expand it in this way. So change in the input, change in the output, and eventually 3 delta x over delta x, and it becomes 3. And if you take the derivative of this function, where change in the input, change in the output, and eventually this becomes 2x plus delta x, and this guy goes to 0. So you end up with having just 2x. And well, here comes some common derivative rules. So first of all, well, this is probably the first time you've seen Euler's number. So in the high school, when you study calculus, we also study Euler's number that is notated with E. In other words, this is the base of natural logarithm. So this is a number. This can be expanded as 1 plus 1 over n to the n. And that is equivalent to 1 over m factorial. And eventually this is kind of an irrational number. And this is some special constant. So this gives us some derivative rules like this. So taking the derivative e to the x is e to the x itself. Where if you had e to the ax, then derivative of this guy is a multiplied by e to the ax. Log base of ex becomes 1 over x, and the derivative of log base bx is where this is some kind of general rule for logarithm. One thing I would like to give a note about this Euler's number. Euler's number is actually a special number representing the natural growth. So what it means. Imagine you have a benevolent bank. And if you give them some money, exactly 1 year later, it becomes twice. So where you have a given time, 1 year, initially you invested a certain amount of money. 1 year later, it's going to be twice. You looked at this scheme, interest policy, and you asked some kind of changes, something like this. Let's divide the 1 year span by half and give me 1.5 times of my original investment after 6 months. And after 6 months, give me another 1.5 times of it. Well, this sounds well reasonable. But let's try to measure the amount of the total interest that you get. So that this is going to be twice of my original investment. This is going to be 2. Well, I not exactly remember, but it's going to be 2.1 or something. So this is slightly larger than the original interest. Well, let's try to make another deal. So instead of taking 6 months span for the interest, let's take it 3 months. And instead of taking 1.5 times of the original investment, at the end of the year, you will get 1.5 to the 4 and the original money. And it's going to be larger than 1 year span and 6 months span again. So you do it again and again. And eventually, well, you're going to get the interest money where sort of continuous time base. So it's going to be generalized in this way. Something like this. So in the first case, it's going to be the original money and after 1 year. And this is 2 times of the original investment. And number 2, 6 months span, it's going to be something like this. So 1.5 to the 2. So it's going to be 2.1 something, and this is larger than 2. This is larger than 1 and larger than, larger than 2, larger than number 1. And so on. So where if you increase this to the infinity, it's going to be written as like this. And this is when you get back after 1 year, if you get continuous interest over time. And this is what natural growth rate is meaning. And Euler defined this as E. The definition of E comes from this kind of calculation. Just a side note. So again, the same definition here, and if you calculate that, it's going to be 17, 1828, 1828, 1828, blah, blah, blah. So that was a Euler number. And let's move on to another properties of derivatives. So where derivatives are linear, that means where if you have sum of 2 functions and take the derivative, that is equivalent to derivative of the first function plus derivative of the second function. And also it is linear, so it has a scalar multiplicability. So where if you have GF, G is constant. And C times F derivative is equivalent to C times F derivative. So for example, if you have 2 minus x to the 2, where you can expand it in this way and take the derivative of each term, and you will get the result. Where similarly, if you have 2 f to the 2, 3x, and 1, take the derivative of each term, and you will get the result. So that's straightforward. And this guy involves in a Euler's number. So take the derivative of each term, the constant becomes 0, and e to the minus x becomes minus e to the minus x. And there are some rules related to product. So if you have 2 functions and take the derivative of its product, and it becomes where derivative of the first guy and the original function itself, and the original function itself and derivative of the second function. You can also consider where division of the 2 functions. So if you take f over g to take the derivative and you will get this result. So the dividend becomes power of 2, and you are sort of interchanging where take the derivative of f, multiply the original function g, negative original function f, and take the derivative of g. So here comes some example. So e multiplied by x to the 2 plus 1 power of 2 can be written as the two term repeated. So taking the first guy prime, taking the second guy prime, then calculation becomes very easy and you get the result. And here is a fractional where one function over the other function. So we're taking the dividend, take the power of 2, and take the first guy prime, take the second guy prime. You want to find the difference between them, and you will get the result easily. The rules are summarized here. And well, here is a special function called sigmoid. So sigmoid will come along when you study logistic regression and when you study some activation function in neural network. Well, anyhow, sigmoid function can be defined as 1 over 1 plus e to the minus x. And if you take the derivative of this guy, well, taking the derivative rule is easy. So dividend power of 2 and taking f and g interchangeably, and you will come to have this guy. And if you try to find the original form of this guy, well, this is equivalent to one over 1 plus e to the minus x, e to the minus x over 1 plus e to the minus x. So you can easily come along with this form. So original sigmoid function multiplied by 1 minus the sigmoid function. And this sort of rotating pattern, so where if you take the derivative or if you play with sigmoid function, where you can reorganize the equation in terms of the sigmoid function again. And this kind of rotating property is used a lot in machine learning. And let's move on to the derivative of vectors and matrices. So, well, from now on, we want to play with matrices. And if you think about matrices, well, try to think about system of linear equation for the first time. So you have set up a coefficient. And here are your unknowns. And here comes your target value. And we want to take the derivative of unknowns mostly. Where first of all, this kind of function or this kind of matrices and lots of unknowns are difficult to deal with. The reason is it is very difficult to visualize. For example, if you only have 3 unknowns, like x1, x2, and y, where you stop all the 3-dimensional spaces that we can easily imagine in our brain. So if you have any more unknown value, it's really difficult to visualize them. So if you directly apply the idea of derivative, well, maybe the definition is closer to what we call as total derivative or full derivative. So if you have a function with 2 unknowns, so ax1 and bx2, in this case, taking the full derivative of the function becomes adx1, adx2, and eventually, if dx is going under df and going under this guy. So you are basically dividing the equation with dx1. So df over dx1, dx2 over dx1. And well, this is just a constant. So you are taking the derivative on all different unknowns. But in machine learning, we use partial derivative much more. So partial derivative can be understood in this way. So you have multiple input. And you have a single output. Given these two, you want to measure the ratio between the change in the output, over the ratio between change in the input. So if you want to consider all different unknowns in the input space, then that corresponds to the total derivative. But in the example here, we have two unknowns. Maybe we want to measure the ratio between output and only one of the unknowns. And that corresponds to the definition of partial derivative. And this is what we use much more often. If you do so, you originally have ax1 and bx2 is equivalent to x. If you take the partial derivative with respect to x1, this is read as round, so round f over round x1, where you are considering bx2 as constant. And you only consider these two in the derivative. So to be more correct, I should use round. Simply, you're taking dx1, so simply a, where it's just a waste of writing, but where this is for the first time, so dx2 is equivalent to bx2, dx2, so it's going to be b. So on page 10, where this is sort of more formal definition of partial derivative, you can actually come along with the input variable on top instead of input variable on the bottom. Where again, in machine learning, we use the second definition much more. So we usually look at the output space compared to every individual input space. And we use this a lot when we try to fit the model parameter to some data. So we are going to discuss this a lot. So at this moment, try to familiarize yourself with the notations. So here comes some additional additional principles related to partial derivative. Just take a look and you will get a sense of it. So those bold spaces are vectors, and uppercase letter, these are matrices. So make sure you read those properties and understand each of them. And here are additional description about partial derivative. These are basically what we have discussed. So changes in the output, changes in one of the input, and they can be expanded more formally in this way. So this is a change in function with respect to one of the variable. And taking the difference between the change and the original function value. So here comes some example. You have a function that is 3x1 square and x2 square. But if you take the derivative with respect to x1, the second term, x2, is considered as constant. You're only considering the first term. And square becomes 2 in front of the term. So you're going to multiply 3 and 2. That is 6x1. And if you take the derivative with respect to x2, then vice versa. So you're taking the first term as the constant, and you're only considering the second term. And it's a power of 2, so basically 2 multiplied by x2. Notation-wise, we often rewrite some function using some other simpler variable. So we're replacing f blah 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 with some other simpler variable like z. It's quite common in machine learning as well. So you will see this kind of notation a lot more common. So g is defined as w1x and w2x2 and b. In this case, if you take the derivative of g with respect to x1, everything is constant and it is read by coefficient. So it's going to be very simply w1. Well, if you take the derivative of z with respect to b, where everything else is just constant, so it's going to be 0, and b prime is simply 1. So this is how you treat the partial derivative. So we have seen different notations so far. So in the previous slide, where I have used the different types of notation. So one is df over dx. And this is read like delta f and delta x. Delta usually meaning the change of the variable value. So you want to measure the change of f over change of x. So where things are straightforward. And Newton has used the same f dot to mean the same thing. And Euler has used the capital D. And Lagrange has used the f prime, where I personally use f prime and df dx a lot. And again, d and delta usually used interchangeably. And later on, you're going to treat with Rashov partial derivative. So in the previous example, if you take the partial derivative of function z, you end up having multiple outcomes that depend on the number of the input variable for your function. And well, if you want to write the result of partial derivative all the time like this, it's going to be quite lengthy and it's not really easy. So people eventually write things in terms of a vector. So it's going to be represented as W1, W2, B. And since this is the result of partial derivative, so these are sort of independent value. So to represent that, we use this upside down triangle. Right, let's move on to the chain rule. So chain rule, but there are sort of a gap between the terms that we use in Korean, especially in middle school, high school. And this is something called as 합성함수. But at least for me, where I cannot see the clear connection between 합성 and this kind of thing. So this is actually chain of the function. So you calculate a function and take the output and put it in another function. So that is a chain of multiple functions. And if you have such thing, so f of g, x, where we have a special rule for taking the derivative, and that is called as a chain rule. So what this stage is actually easy. So if you have f of g of x, taking the derivative of x, then it's going to be taking the derivative of outer function, and the inside one comes out of it, and you again take the derivative of the inner one. And this can be understood as someone like this. So while you are doing this, what you are essentially doing is sort of substitution. So you first taking the derivative from x to u. So this can be understood as gx. And where at the beginning we had f of u. So we are taking the derivative of f of u for the first time. Then we are taking u and take another derivative of u. So it's going to be taking the derivative of gx. So well, conceptually, what you are essentially doing is taking this multiple step, and we normally memorize this kind of rule and apply it much more easily. And this expands to multivariate functions as well, or multiple chain of functions as well. So well, if you have three different functions cascaded, so f of g, of h, of x, and you're simply multiplying multiple derivative in one derivative operator, and it's going to be taking f prime, taking g prime, taking h prime, and so on. And this chain rule occurs a lot when we study especially backpropagation algorithm with a neural network. So backpropagation algorithm is how to fit the parameters for neural network. So we have original input x1, x2, maybe more, and each of them taken as a linear combination of weight. You have multiple weight for multiple input, and each of them aggregated to another layer. And at the another layer, you're taking the summation of all those outputs from the previous layer, and you're taking a special function that is called as activation function. And basically, the neural network has this simple structure repeated over and over. So you have layers of some number, taking the weighted sum or linear combination of those values, and taking the activation function, and again taking the weighted sum, taking the activation, and so on. So this is a cascaded or a chain of those multiple functions. And well, it sounds very complex, but at the end of the day, what you apply according to the backpropagation algorithm, you're simply taking the derivative of the final outcome and cascading back some quantity. So we are going to see how this backpropagation algorithm works later on when we study neural network. Let's move on to functional approximation. So, so far we have discussed where we can take derivative of a function and we can write f prime down in terms of this expansion. Notice that we are sort of putting the limitation to delta x close to x. So maybe this is a very small value because we're pushing this value towards 0. So maybe we can just remove this. We'll still get the similar result like this without limitation, like this. Well, after that, you can just reorganize the function. So collect this guy multiplied by this guy. So f prime x multiplied by delta x. And you want to push it to the other side of the equation. So plus fx, that is approximate to f of x delta x. And again, well, this is a very small value. So this is somewhat negligible. And we can say where the change in the output space is almost similar to where some value calculated at a certain point. So this approximation makes sense. Now try to understand what this means using the example. So say fx is e to the x and x is getting close to 0. So in this case, if you use the formula that we came up with, so fx plus delta x is approximate to fx plus f prime and multiplied by delta x. If you do so, we can write things down in this way. And try to find this meaning at a certain point in the function. So we want to apply what we came up with and try to find the actual value at this point, x is equal to 0. And still, we don't know what this value, so we assumed this guy is getting close to 0, but we cannot omit them clearly. So let's replace it with some unknown value. If you do so, this guy is going to be e to the x, 1, x. And this means, well, you have original function, ex. So this guy coming from here. And you have approximated function that is simply 1 plus x. That's over here, green line. So obviously, if you look at the global shape of these two functions, well, those two functions are different. But what we want to focus on is the value at this point, this specific point. So what this approximation means, well, if you assign certain value to what we obtained over here, well, maybe it does not work in the other area like this, but at certain point here, these two are almost the same. So you can approximate this sort of complicated function e to the x equal to 0. So one can approximate this complicated function with much more simpler form. This is one of the approximation technique that we can use by taking the derivative of the function. And well, you probably heard of this Taylor series. So from the machine learning point of view, what we want to extract from the Taylor series is well, function approximation. So Taylor series formally defined in this way. So you have given a function fx. This can be infinitely differentiable. So fx can be expanded in this way. So you take the original value of f at certain point a. And you're taking f prime over 1 factorial and multiplied by x minus a. So you can understand this as delta x. And you taking the derivative of the original function. So this is one derivative, sort of. And you're taking the second derivative after the second term. So that's going to be like this. And taking the third derivative, that's going to be like this, and so on. So, well, what we studied from the high school and maybe in the first year of college, well, Taylor series is basically defining where you can expand the original function, fx. And if you want to calculate the certain value at certain point, where you can approximate that computation by expanding the original function in this way, and after that plugging the value in, everything will be very easy. Because well, things are very clear in this expansion because well, differentiable at x, then eventually you want to put x in every other well, factor there, and obviously it becomes 0. So you ended up having fx or something like that. So you probably remember all this. But the main idea that we want to extract from Taylor series, where we can approximate some complicated function with a much more simpler form. But after that, at this point, where instead of playing with this guy, we can play with the 1 plus x. So that's the main idea that we want to learn. So the diagrams on this slide is basically showing if you take the first derivative of this blue line, so that's going to be tangential line. So that will be like this. If you take the second derivative, where it's going to be where showing the acceleration in the change in the function. So it will be like this, where the point that we want to focus on though, where say this is the point that those two lines where I'm keeping meshing the space up. So this blue line and red line, they are meeting a certain point. They are meeting a certain point. They are meeting a certain point. Where maybe you want to represent the value of the function at this point using the first term. And this will cover the most of the value that you are calculating. And you still have some remainder, but they are almost negligible. And that is important because it gives us a lot of motivation for the optimization. So optimization is the crucial thing in machine learning. So eventually we have set up data and we have some template for function. And it has multiple parameters or weights. And based on the observation value, we want to set the parameter value or weight value. And the operation based on the data, we want to run the parameter or we want to fit the function. I'm going to write things down a bit. So we have data. And based on the data, we want to fit the function. So well, this process is actually the process of optimization. So we are going to see why optimizing a function is actually running the data using the function. But at this point, let's simply discuss that where we have a function fx, and eventually we want to find some spot that is the minimum value across entire the domain of the function. So you have a function that shapes like this blue line, and you want to reach it to a point that results in the minimum value. So this is called as the process of function minimization, finding this spot. Function minimization. And the way we find this minimum spot is basically using the derivative. So if you take the derivative that is representing the tangent line. So if you draw multiple different tangent line, well, you can at least measure this is going up or this is going down. Now let's imagine you want to find a spot like this. So all those spots, they are sort of going up and down, going down and up. So if you measure the picking point of each, then the derivative value becomes 0. So tangent, the slope of the tangent is 0. So that will guide us how to optimize a function. So we want to find the spot that is resulting in the tangent line. The derivative value is 0. But notice that it is just a necessary condition. So even if you find something prime is 0, that does not mean that it's what you want to find as an optimal. What that means is, well, you actually have multiple tangent lines that result in the slope becomes 0, right? So that's what we just found out. Well, one additional condition is where we want to find the minimization function. So we want to also measure the double prime is positive. Double prime means acceleration. Where something is positive, you're actually going down, going down, going down, going down, but the ratio of the change is actually turning to the positive. So the acceleration at this point is negative. So you're going down. But after some point, your slope is 0. After that, your acceleration is turning to positive. So the slope is negative here and slope is positive here. So at least within this span, the acceleration prime, double prime is positive. So while you are doing this, that means your original function shaped as a convex. Within this period, if you find the f prime becomes 0, then it's going to be a possible minimum. So where we are talking about two conditions and try to making sense of the geometric meaning of this condition. But still, you have multiple of these. So you have double prime positive and prime 0. You have double prime positive, prime 0. So you have multiples of these in your function. So this is two useful conditions, but still these are not sufficient. These are just necessary. So that's what this slide is basically meaning. And speaking of the maximization function, so far we talked about minimizing the function f. Sometimes we want to maximize the function. Well, if that's the case, instead of this and this, we want to find one of these spots. And again, the condition is very similar. You want to find the tangent line slope 0, and the acceleration is essentially negative. So where you're turning the velocity from the positive to negative, positive to negative. So your double prime becomes negative. So this is, again, necessary condition to maximize the function. So like this, you have multiple candidates for maximization, or minimization. And this is a sort of natural observation that you will experience a lot. Since we have multiple potential minimum, we call all of them as a local minimum or local maximum. But only one of them should be the smallest. Only one of them should be the largest. And this is what we want to find in open cases. And this is called as a global minimum. So out of multiple local minimum, you really want to find global minimum. Or vice versa, out of multiple local maximum, you want to find only the global maximum. So essentially, what we call it learning is feeding the data in this kind of function space. There are multiple techniques to get the global maximum better. Or sometimes where you have a learning algorithm that is prone to find local minimum only. So if you're lucky, you will end up with a global maximum, but you still have a chance to find local maximum or local minimum. So we will see this kind of thing over the semester again. But at this point, the important thing is to understand this entire framework. So learning something using function is optimizing a function.